it has come. You've reached the hardest questions of grade 11 physics. All right, just to give you a bit of context of why these are hard, let's take a look at this example here. Okay, of the following, which one is easier to answer, A or B? I think you guys already know that. The answer A, right? It's easier to add 2.2 plus 3.3 to get to your answer than trying to do the problem over here, which then in your head you have to do this mental exercise of subtracting 8.1 by 3.3 to get to your answer. Okay, and then you have to stop and think a bit longer. Well, this is just a scalar problem. Now there's a problem where there's no direction involved. It's not that bad to add and subtract in your head. But in today's example, since we're dealing with vectors, which may go off in these skewed directions, things get a lot more complicated. All right, let me visually show you. Okay, what's easier to solve? This green vector over here, or is it easier to solve for the mystery meat here, or even the mystery meat over here? Which one's easier? Addition is definitely going to be easier than trying to solve for the not so easy part. Okay, and you'll see what I mean in today's example. We'll start off with this classic story of Calvin and Susie. Calvin being a young little boy, being really weird, and you'll hear this all the time. All right, boys are so weird in their ways of showing their affection. If they like a girl, they're going to do something crazy, like tug on their hair or whatnot. As for Calvin, he wants to say hello to Susie by doing some math, calculating it out, and trying to square her right on her head. Of course, I think either his math is off or his shooting's off, because he doesn't end up hitting her. I like this problem because there are some numbers involved in it. And yeah, I geeked out. I sat down and took those numbers and converted them into standard MKS notation. Yes, I did that. I also had to add in something really weird because I had to also emphasize that the snowball is propelled with some fuel. All right, and this is just one of the realities of solving these problems over here. For one thing, if the wind did not create any wind resistance, if you toss an object and the wind's blowing this way, the object will definitely go across. Make sense? So you need the air resistance. But you also know that air resistance slows things down. So in other words, if I toss an object and I blow wind at it, it's going to slow down and come to a stop and eventually carry the opposite way if it wasn't for gravity. So we want to ensure that this object over here is able to maintain its same speed relative to the air. So it's kind of like you walking on top of a deck of a ship that's moving, right? You're still able to accomplish that. So in this example here, I have to give the snowball energy in order for it to maintain its constant speed with respect to the wind. Okay, now let's solve this problem. And this isn't the harder one, by the way. This is as straightforward as your last day's lesson, except that you're dealing with a scalene triangle. So you can solve this either by component method or by trig method. Preference is up to you. They'll both take just as much time in solving. In this example over here, it looks like I solved it by component method. All right. So what I did was I took this vector over here and I broke it down into its horizontal and vertical components. In the second vector, I also broke it down into its horizontal and vertical components. Quickly going through this, we see that VBW is just traveling towards the west. So that's it. All right. So 40.2 meters per second towards the west. As for the second one, I see that this component over here is opposite of 15, so I'm going to multiply the hypotenuse by the sine of 15, like so. Negative, positive, negative wins. Rinse and repeat in the vertical dimension. VBW does not have a vertical component, so really my solution is the hypotenuse times the cosine of 15 degrees. Glue them together by using the Pythagorean theorem. Solve for the angle by using inverse tan. And there's your answer. Doesn't matter if you solve by component or by trig. Try them both out on your own. However, the more challenging part is, what if he needed to calibrate his setup so that he can actually greet Susie right on the head? Okay, so we need a bit more context to this problem. So let's say that Susie's located 50 meters north 74 degrees west of where Calvin is. How should he aim the snowball so that when the wind catches it, it'll still be directed towards her head? In this problem over here, it actually is way easier to solve by using trig method. That's why we go through this exercise. Because if you try solving this by component method, oh, it's a nightmare. And you'll see what I mean very soon. All right. Okay, so if you're going to solve this by trig method, you'll want to draw a sketch. Remember this green vector is the resultant vector. Now the 50 meters is a distraction. We're only dealing with velocities here, but the angle is still true. After all, as I said from before, if you're traveling this way, the only place you'll end up is in this direction. It's impossible for you to end up over here if you're traveling this way. All right, so the north 74 degrees west is relevant. Susie is located somewhere over here. Okay. Now the wind in this case over here, it's still the same as before. It's blowing north 15 degrees towards the east. All right, so there are crosswinds that go like this. Now if Kelvin actually decided to launch the snowball in this direction, in accordance to this green vector over here, it would not hit Susie's head. Instead, the wind would carry the snowball and it'd probably be going somewhere up there. I hope that makes sense. All right. So the only way for it to smack Susie's head is if he went against the wind. And that's how you construct your triangle. All right. Think about it, not oppositely, but you probably want to have these field vectors showing you the direction of the wind, and you want to fight against the wind. Or the water current, and you want to fight against the water current itself. Now we're not going to draw all the field vectors because that's just a big mess. We only need this vector over here. Make sense? Just like from before? Okay, just draw the second vector if that's the second vector. Make sure the second vector points to the resultant vector. From here, it's fairly straightforward to draw your very first vector, the velocity of the object relative to the wind. A few things I want you to do before you move forwards. First off, create the formula for this, right? So VBG is equal to VB to the wind plus the velocity of the wind to the ground. Once you created the formula, make sure that's grammatically correct. Are adjacent subscript letters beside each other? And are the leftover letters used to describe the big picture at the end? If it is, you're good to go. If not, rinse and repeat. Next, make sure that this formula over here matches up with that. It should match up, because if it doesn't match up, you've connected it incorrectly. All right. You'll see that VBW is the first vector. Done. Connected to the second vector. Good. Is that used to describe your resultant vector? Yes, it is. Vector 1 plus vector 2 head to tail. Resultant vector always points to the last vector drawn. And we're good to go. Now some students might ask, well, could I actually flip this around by starting off with that vector first and this vector afterwards? Technically speaking, yes you can, but you'll see that your angles are all now skewed off, and now you have to do even more calculations to get to the correct angle. Try it out if you don't believe me. Okay, so we're better off just sticking with the system, because at least that gives you rules to abide by in getting to your answer, as opposed to doing your own crazy ad hoc thing. Okay, since everything makes sense right now, next thing we want to do is figure out, well, what do we know really from this diagram over here? Okay, for one thing, VBW, we don't know the angle. We don't know how Kelvin should angle himself, so that is unknown. Okay, but we do know VBG, which is at 74 degrees. We also know VWG's angle, right, which is north 15 degrees towards the east. Well, that ends up creating a very interesting relationship right here. We can, interestingly enough, solve for this angle here. It is possible. So even though this side over here is impossible, this side is also impossible because we don't know where the purple vector should point. It could point like this. It could also point like that. So this angle over here, we won't know. But this angle up here can be solved by using the Z pattern twice. The first time round is by knowing that that angle there is the same as that angle there. I hope you could see the Z pattern if I blow it up. Okay, here's my vector. Here's 15 degrees, so it must be 15 degrees right here as well. There's also another Z pattern. Of this vector over here, this is 74 degrees. So we can actually figure out the sum of those two. 15 plus 74 gives us 89 degrees. Now, because these are all weird vector symbols and we don't want to deal with that, how about you just go off and label each of the vertices? It just makes life easier. It really doesn't matter which letters you choose. All right, these are the ones that are in my PowerPoint. So I denoted this as angle C, this is angle B, and this as angle A. Angle C can be solved by adding 15 degrees with 74 and by using the Z pattern twice. Good. Next, I'm just going to highlight away just so we can visualize everything. We know angle C. VBW? Yeah, we know VBW. We also know VWG. Anytime that you know a side and corresponding angle, you can always solve for it by using, that's right, sine law. So sine C over C is equal to, oh, we're looking for this one, so sine A over A. We're looking for angle A, so we bring this A on top over here and we sine inverse both sides. So A is equal to the sine inverse of little a times sine C divided by C. Crunch everything in, and you can see that this problem over here, it's not that bad to solve. All right, you wouldn't have received full marks yet because this 3.82 degrees is just for angle A. So yes, it is technically true. Wherever Susie is, he just needs to point 3.82 degrees to the left of her. That is true. But if we're trying to represent this as a compass rose or a polar coordinate system, is that what it's called? Then we need to make it relative to north, south, east, west. I forgot the term for it. That's okay. No edits. So to solve for this bigger angle over here, we could see that what we need to do is add 74 degrees with angle A. And then we can have the compass direction. I think that's what I'm thinking of. All right. So 74 plus 3.82 will give you 78 degrees. Therefore, Calvin needs to launch the ball at north 78 degrees towards the west, or west 2 degrees, or sorry, west 2 degrees, west 12 degrees towards the north. That's it. And you can see that's not too bad to solve now. All right. So the biggest challenge about these problems over here, you may want to just rewind the video if you want to hear it one more time, is setting up the triangle. Because if the triangle's set up wrong, nothing else will work out. So my recommendation is to draw your resultant vector, then have your second vector point to the resultant vector, because often you're looking for this first vector. Or you'll have sometimes in your homework, these two are given to you, fine, and you're solving for this one. In any case, use this formula over here because that will give you the structure and how you should approach the problem thereafter. Where often the easiest way of solving it is just by using sine law, and that's it. You're done. Maybe cosine law because you need to find out how long this is or how fast is the ball actually traveling at. Aside from that, that's it. Now you can stop the video now, or for those that really want to know, can you solve this problem by using the component method? Yes, you can. I've had kids bug me about it, and it took me forever to solve. So let me just PowerPoint away the answer to you. All right, I don't recommend this method. First thing you probably want to do is to draw out your sketch as you did before. Break down everything into its horizontal and vertical vectors so that you can now start to write out your equation. Your equation will be based upon this formula here, where you'll start off with x, 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 and then you'll erase it, followed by the same formula, but with the letters y afterwards. We'll start off with the ones with the letter x first. Okay, VBGX, so this vector over here. We don't know what that length is. Okay, we may know the angle, but we don't know what the length of this is. To represent this vector over here, we'll have to multiply VBG by the sine of 74 degrees. Agree with that? On top of that, because it's pointing towards the left, that's why in the formula you have this minus sign here. As this is all PowerPointed out, I'll just leave it there, but you can still follow along with me. As for VBW, well, because we don't know the angle here, we only know that this is equal to the hypotenuse times, well, that's right beside, the adjacent or the cosine of whatever that mystery angle is. That's all we know. The only component that we know for sure is this little red vector up here, which is equal to the hypotenuse times the sine of 15 degrees. So far, so good? Well, this leaves us with a little bit of a conundrum because we have an equation with two unknowns. So we have no choice but to pause. We move on to the y dimension. All right, as stated from before, we don't know how long this is. We just know that it's going to be equal to the hypotenuse times the cosine of 74 degrees, like so. Same is true with this vector over here. We don't know how long it is, but it's equal to our VBW, which we do know, times the sine of some mystery angle. We don't know. The only vector we know for sure is this little blue vector, which can be solved mathematically. So this leaves us with two equations with two unknowns, which in your head, because you just made it through grade 10 math with linear systems, that's not too bad to solve, is it? Two equations with two unknowns. You can solve either by substitution, elimination, or by division. All right, in this case over here, well, it's going to get messy. All right, yeah, there's two VBGs, so we can equate them together, and it'll start to look something like this. All right, well, next thing we should do is expand, collect like terms, and simplify as much as you can possibly do so. But no matter how hard you try, you'll end up getting this. Sine of theta and a cosine of theta is equal to this. So how in the world do you solve it? There's many different ways of doing it. One of them is by knowing this interesting trig identity, where the cosine squared of theta plus the sine squared of theta is equal to 1. It's one of the many identities you'll learn in grade 11 and grade 12 math, or in the world of trigonometry. So if this is true, then if you're trying to solve for sine, then sine by definition is equal to the root of 1 subtract cosine squared theta. And that's how I'm going to incorporate it here. Or the other way around. Cosine is equal to 1 minus sine squared theta. Okay, now we have a square root in our equation, so how do we get rid of the square root? There's only one way around it. Placing the square root on the other side, and then squaring both sides. There is no shortcut with this. So we deal with that, and we expand it out, and we try to simplify as much as possible, but now we're on to another problem. Now we have something that's represented by sine squared, something represented by sine, and something that's linear. Doesn't that look familiar? Something that's ax squared plus bx plus a constant is equal to 0. You guessed it. We got to go off and do that. So you sub everything in, you go through your number crunching, you'll find out that you'll have different possible answers. Then you have to do the sine inverse, find out which one is logically correct. And yeah, you can get to the answer. That is true. If you want to do it this way on a test, by all means, but work smart and hard, but work smart. Catch you in the next episode.